Well, hello and welcome to this very interesting exercise, very interesting numerical example related to electromechanical conversion systems. And something that is extremely important to understand when we are working with generators is the induced voltage. So if you remember from the theory, I already explained over there that when we have a conductor and this conductor is moving inside a magnetic field density with some speed, depending on the direction between the conductor and the magnetic field, there is a possibility of inducing a voltage or an electromotive force. So this example today is to explain and to complete a numerical exercise related with this topic. So without further delay, let's start reading this statement over here. Consider a straight cylinder conductor whose radius is too small that it can be neglected. So what I am telling you is that we can imagine this cylinder over here is a conductor, but the radius is so small that you can imagine that this is a straight line. So this conductor, the length of the ideal conductor is 75 millimeters. What I'm telling you is that from here to there, they are 75 millimeters. The conductor is located in a uniform magnetic field flux density. You can see over here B equals 0.6 Tesla. When the conductor is moving in perpendicular to the magnetic field at constant speed, an induced voltage of 9.0 volts appear. In other words, when you can see over here, there is a blue vector that is going from the top to the bottom, and that is the direction of the magnetic field density. So when we have here the conductor, and the conductor is moving perpendicular to the magnetic field density, in other words, when we have here 90 degree between the velocity and the magnetic flux density, so there is induction. And this induction between this point 1 and 2, if we connect over there a voltmeter, there is an electromotive force E that appear between the contacts. So we are talking about 9 volts in this very specific case. But now the magic question. If we know that the magnetic flux density is 0.6 Tesla, if we know that the length is 75 millimeter and the induced voltage is 9 volts, now the question is, what is the velocity of this conductor in order to induce the 9 volts? So this is a very simple example. This is something that is extremely simple for my students. You can see over here the result. If you want to attempt this example by yourself, is 20 meters per second. So the very important aspect here to remember is that there is a very clear equation that is defining the electromotive force induced by the moving conductor inside the magnetic field. As you can see over here, I have the equation number 5, but this equation number 5, you need to be careful because if we say theta is the angle between V and B, this equation is only valid if we have 90 degrees. So in this case, we are okay because they are 90 degrees between the magnetic flux density and the velocity, and the equation says something very simple. The induced voltage is proportional to the magnetic flux density, the length, and the velocity. In this case, if we want to obtain here volts in the induced voltage, well, we need to use the MKS system for all the units. So remember meter, kilograms, and seconds. So for instance, for the magnetic flux density, the unit must be Tesla. For the length, we need to use meter, And for the velocity of the conductor, we need to use meters per second. So what we need to do now is, in this problem, we are interested on calculating the velocity that is inducing 9 volts in that conductor. So it's very simple, starting from this equation number 5, to extract the conductor velocity. And what we need to do is divide the induced voltage by the magnetic flux density and the length. And voila, we obtain here this beautiful equation number 6. The velocity will be the induced voltage divided by the magnetic flux density and the total length of the conductor inside the magnetic field. So now is just a basic numerical substitution. Because we are using MKS system, remember the following: the length of the conductor, the length of the conductor was 75 millimeters. So we need to convert this into meters, and that is dividing by 1,000. So here at the top, the numerator, we can find the induced voltage, 9 volts. You can see here in the denominator, the magnetic flux density, 0.6 teslas. And basically here, the length that is converted into meters, 0.75 meters. So voila, we calculate, and the result is 20 meters per second. So this example is very interesting and very illustrative, because at the very end, we can conclude over here that if we have a conductor, and this conductor is 75 millimeters or 0.75 meter, and we move with a constant speed of 20 meters per second inside a magnetic flux density of 0.6 teslas, well, the induced voltage between the terminals will be the magic number 9 volts. So this is a very basic but very important exercise, numerical exercise, because here you are using this very important equation over here, and the equation is basically defining the induced voltage over a conductor that is moving inside a magnetic field. And you must remember this equation again: the induced voltage, equation number 5, is only valid if there is a perpendicular movement between the conductor and the magnetic field. If that is not the case, of course, we saw that equation in classes. There is a sign of the angle between the velocity and the magnetic flux. But we will cover that later in another example. So this is all for this exercise, for this numerical example. I hope you enjoy. I hope that you understand the basic concept of induced voltage and MMF inside this conductor. And I hope that you understand and enjoy the explanation. If you have any question, please drop a comment or basically send me one email. I will be extremely happy to help you. And if you like the video, please like the video or subscribe to the YouTube channel. Thank you very much for watching, and I will see you at the next one. Bye now.